Welcome to the deep dive. You know how everyone's looking for an edge in the stock market?
Always.
Today, we're cutting through the noise and getting straight to some really fascinating research on predicting stock prices.
Mm-hmm.
Forget the crystal balls. We're diving into a study that used a really specific kind of data. Insider trading.
Exactly. And for you listening, insider trading is basically when people with confidential, non-public information about a company, well, they buy or sell its stock.
Right.
The thought is, these folks might have a better sense of what's coming down the line for the company.
So their trades could be a signal.
Yeah, potentially a valuable signal.
Right. Think about it. If a company's CEO suddenly buys a huge chunk of their own stock, it could be, well, a strong vote of confidence, right?
That's what feels that way.
On the flip side, if they're selling, it might raise some eyebrows.
For sure.
Now, the study we're digging into, it's called a comparative study of machine learning algorithms for stock price prediction using insider trading data. It takes a really interesting data-driven approach.
Yeah, it tries to see if we can actually use this insider activity to predict where a stock might be headed.
So not just gut feeling about the trades.
Exactly. Instead of just relying on that intuitive feeling, the researchers used machine learning.
Okay, ML. Tell us about that.
They took historical insider trading data for Tesla, specifically from April 2020 to March 2023.
A recent period, then.
Yep. And fed it into different algorithms to see which ones could best spot patterns.
And predict future stock price movements based on this insider activity.
Precisely. So our mission today is to pull out the crucial findings.
Oh, yeah.
Which of these digital tools worked best? What kind of insider information turned out to be most important?
And what does all of this tell us about how the market behaves? Or at least how this part of the market behaves?
Good point. Yeah.
Okay, so the core idea makes a lot of sense, right? As we were saying, insider trading data could potentially give us a window
Into what the insiders are thinking.
Yeah, the people who know the company best. If top execs are loading up on shares, that certainly feels positive.
And selling. Maybe not so much.
Right.
But what's really interesting is how this study moves beyond just that basic intuition.
How so?
Instead of just looking at individual trades, they used machine learning to try and automate this prediction process.
Automate it. Okay.
These algorithms are designed to learn from massive amounts of data, identify subtle connections.
Things a human might just miss.
Exactly. And potentially forecast stock price changes in a much more systematic way than, say, a human analyst could manage on their own.
It's like training a superpowered detective.
Yeah. To find clues hidden in mountains of trading data. That's a good way to put it.
So they put a whole team of these digital detectives to work. What were the main types of algorithms they tested out?
Well, they looked at a range of algorithms, from simpler ones to some pretty sophisticated techniques.
Okay.
First, they used decision trees. You can imagine, like a flowchart.
Simple if-then steps.
Kind of, yeah. Each decision point is based on a piece of data, leading you to a prediction. Then they used random forests.
Which sounds less simple.
Yeah, well, they're essentially a whole bunch of these decision trees working together.
Yeah.
An ensemble.
Safety in numbers to get a more reliable prediction.
Potentially more robust, yeah.
Okay, so those sound relatively straightforward, conceptually at least. What about the more complex methods they explored?
Right, that's where support vector machines, or SVMs, come in.
SVMs, heard of those?
They're really powerful tools that can handle complex data sets. Think of them trying to find the absolute best way to separate different kinds of data points.
Like drawing a line between buys and sells, maybe?
Sort of, but it can be much more complex than a straight line. For this study, they specifically looked at SVMs using different kernels.
Kernels.
Yeah, mathematical functions. They tried linear, polynomial, and radial basis function, or RBF.
Okay, break that down. Linear, polynomial, RBF.
So imagine you're trying to draw that line to separate groups of data. A linear kernel tries a straight line. Simple, got it. But if the data is more mixed up, a polynomial kernel can draw curves.
More flexible.
And the RBF kernel can create even more intricate, complex boundaries.
So that added flexibility might help find trickier patterns.
That's the idea. Often helps achieve higher accuracy. But there are trade-offs.
We'll get to those, I bet. Different tools for different levels of complexity in the data.
Yeah.
And there was one more type of algorithm, wasn't there?
Yes, K-means clustering. Now, this one's a bit different.
How so?
It's an unsupervised learning method.
Unsupervised. Meaning?
Unlike the others where they were trying to predict a specific outcome, like the stock price direction, K-means just tries to find natural groupings or anomalies within the insider trading data itself.
So it's not predicting, it's pattern finding.
Exactly. The idea is that unusual patterns in this trading activity might then signal upcoming changes in the stock price.
Like looking for unusual blips on a radar screen.
Yeah, exactly. They might indicate something important's about to happen.
Now, the study didn't just look at any company. They zeroed in on Tesla. Why Tesla? Seems like a popular choice these days.
It is, and that's a really important point.
Mm-hmm.
The researchers actually examined insider trading activity for several well-known companies.
Oh, who's on?
Giants like Goldman Sachs, Facebook, Google, Twitter, even GameStop.
Wow, quite a list.
During that same April 2020 to March 2023 period,
Mm-hmm.
what they discovered was that Tesla had, well, by far the highest number of insider transactions during this time frame.
Ah, okay. So more data points for Tesla.
Exactly. For machine learning to really work its magic, it needs a good amount of data to learn from.
Makes sense.
And Tesla's high training volume just made it the perfect candidate for this kind of analysis. More data often leads to more reliable results.
Got it. More data for the algorithms to chew on. Now, before they could even start feeding this data into the algorithms, there was a crucial step of getting it ready, right? Prep work.
Absolutely. Data preparation is, well, it's often the behind-the-scenes workhorse of any machine learning project. It can take a lot of time.
What did that involve here?
Several key steps. First, they cleaned up the raw data,
Meaning?
identifying and removing any missing or, inconsistent information. Errors, basically.
Okay.
Then they normalized the features.
Normalized.
Yeah, basically scaling all the different data points to a similar range
Why do that?
so that the algorithms don't give too much weight to variables just because they happen to have bigger numbers. Puts everything on a level playing field, sort of.
Ah, okay. That makes sense.
They also stripped out any data that wasn't directly relevant to their analysis.
Like what?
Things like the unique transaction ID, the stock symbol.
Right, they were only looking at Tesla.
Exactly. And certain transaction codes that didn't represent actual buying or selling by insiders.
So they were essentially filtering out the noise to really focus on the important signals within the data.
That's the goal.
What specific pieces of information about those Tesla trades did they end up analyzing? What were the core variables?
Okay, so the core variables they focused on included the date of the filing and the actual transaction.
Two different dates sometimes.
Yeah, there can be a lag.
Yeah.
Also, the name of the insider involved, the total number of shares that were traded.
Size of the trade.
Yep. The change in the insider's overall holdings after the trade, and of course, the price of the Tesla stock at the time of the transaction.
But they didn't just stop at the raw data, right? The paper mentioned they created some new variables to try and get even more insight.
Exactly. They created two really interesting new ones.
What were they?
The first was dollar volume.
Okay, dollar value of the trade.
Simple as that. Number of shares multiplied by the price. The researchers reasoned that really large value trades might be a stronger indicator of an insider's conviction.
Bigger bets might mean more. Makes intuitive sense. And the second new variable.
That was type, which categorized each transaction as a buy, a sell, or a gift.
A gift, like transferring shares.
Exactly. And this distinction is important because a gift of shares doesn't necessarily tell you anything about how the insider feels about the company's future prospects.
Not in the same way an actual purchase or sale would.
Precisely.
And it sounds like that type variable helped them really hone in on the core question of insider sentiment. Are they bullish or bearish on the stock?
Exactly right. For the purpose of predicting stock prices based on that insider optimism or pessimism, they primarily focused on those buy and sell transactions.
So the gift transactions were set aside?
Yeah, essentially set aside for the main analysis because they just don't carry the same kind of market signal.
Okay, so they've cleaned the data. They've created these potentially more insightful variables like dollar volume and type. What's the next step? How do they figure out which of these pieces of information are actually the most influential?
Right. Which ones really matter for predicting stock prices? That's where feature selection comes in.
Feature selection.
The researchers use a technique called recursive feature elimination, or RFE,
RFE?
along with feature importance analysis. The basic idea here is to identify which variables in your dataset have the biggest impact on what you're trying to predict.
In this case, those future movements in Tesla's stock price.
Exactly. RFE works by starting with all the features, training the model, then figuring out which feature is the least important.
And kicking it out?
Yep, removing it and then repeating the process. It helps them narrow down to the most predictive set of information.
Okay, so it iteratively finds the heavy hitters. And what did their analysis reveal? What were the most important pieces of insider trading data for predicting Tesla's stock price?
Their analysis pinpointed 4 key variables as having the most predictive power.
Just four. What were they?
The number of shares traded, the transaction date itself, the total dollar volume of the transaction, and the type of transaction buy or sell.
Interesting. Shares, date, dollar volume, and type.
And interestingly, the dollar volume turned out to be the most relevant of these.
Really? The
Yeah.
total value trumped even the number of shares.
According to their analysis, yes. So, for you listening, this suggests that simply tracking if an insider trades might be less telling than tracking how much money they're putting on the line.
Yeah, big moves, big dollar volume could be the real signals to watch.
Seems like it, based on this study.
That's a really fascinating takeaway. So, a large buy or sell seems to carry more weight than a smaller one, even if it's the same person making the trade.
Appears so.
Now we get to the moment of truth. How did these different machine learning algorithms actually perform when they tried to predict Tesla's stock price based on all this insider trading data?
Right, the performance scorecard. The study evaluated them based on 2 main things: accuracy
How often they got it right?
and how much time it took them to make those predictions. Processing time.
Okay, accuracy and speed.
And the results, which they presented in a table, showed some pretty clear trade-offs.
Ah, the trade-offs. Okay, let's hear it. Which algorithms came out on top?
The algorithm that achieved the highest accuracy, at a very impressive 88%, was the support vector machine, using that radial basis function, the RBF kernel we talked about.
88%. That's high. But I sense a but coming.
You sense correctly. That top-notch accuracy came with a trade-off. It also took the longest time to run,
How long?
clocking in at a considerable 28 minutes.
28 minutes for one prediction run.
Well, for processing the data set to train and test the model for that period, the researchers pointed out that while the RBF kernel is great at finding complex patterns,
Which leads to higher accuracy.
right, but it also requires more complex calculations and can be quite time-consuming, especially with a large data set like this. Lots of hyperparameters to tune, solving complex optimization problems.
So, gold star for accuracy, but maybe not the best for someone who needs, like, real-time results.
Probably not ideal for high-frequency trading, though.
What about the other algorithms? How did they stack up?
Right behind the SVM RBF was the random forest algorithm. It still achieved a very respectable accuracy of 83%.
Still pretty good.
Yeah.
Faster.
Significantly faster, yeah. Took about 18 minutes.
Okay, 83% in 18 minutes. Better trade-off there.
Then the SVM with the polynomial kernel also did well, 81% accuracy, and a processing time of 12 minutes.
Getting faster.
The linear kernel SVM came in with a decent accuracy of 77% and was noticeably faster at just 8 minutes.
Okay, 77% in 8 minutes.
Then you had k-means clustering, moderate accuracy 73%, relatively quick, about 7 minutes.
And the simplest one, the decision tree.
That was the fastest by far, took only a single minute.
Wow, 1 minute. But the accuracy.
Lowest of the bunch, yeah. 68%.
Okay, so 68% in 1 minute versus 88% in 28 minutes. That really highlights the classic accuracy versus speed dilemma in machine learning.
Absolutely. It seems like generally the more sophisticated algorithms that can pick up on more subtle patterns tend to be more accurate.
But require more computing power and time.
Exactly. The study even included a visual representation of this. I think it was a scatter plot showing the relationship between accuracy and processing time for all of the different algorithms.
So you could literally see the trade-off.
Yeah, it really drives home the point that there's no single best algorithm, right? The ideal choice often depends on what your priorities are.
Whether you absolutely need the highest possible accuracy or if getting results quickly is more critical.
Precisely.
The paper also mentioned a visual, figure 1, that seemed to support their findings about dollar volume being important. What did that show?
Ah, yes, figure 1. It presented bar graphs comparing Tesla's average monthly stock prices with the total monthly dollar volume of insider trading.
Side by side.
Yeah. This visual comparison was designed to reinforce the importance of that dollar volume variable that their statistical analysis had highlighted.
Could you see a connection?
Well, by looking at the trends in both graphs, you could see potential connections, maybe significant spikes in insider trading activity, particularly in terms of total dollar value.
And then subsequent movements in Tesla's stock price.
Potentially.
Yeah.
It's another piece of evidence suggesting that those larger insider trades, the big dollar volume ones, might indeed be meaningful signals.
So the visual data seem to back up the statistical findings, suggesting that when insiders make big moves with their money, it might be something for investors to take note of.
Seems plausible, based on this specific study.
Now, this study seems pretty promising, right? Showing how machine learning can be used with insider trading data to predict stock prices. But what's the bigger picture here? What are the limitations, things we should be careful about?
That's a really critical question. Crucial, actually. While this study shows the potential of machine learning in this area, it's really important to approach these findings with a healthy dose of caution and consider the broader context.
Okay, like what?
First off, the effectiveness of these ML algorithms is heavily dependent on having a significant amount of good quality data.
Right. The Tesla example worked because there were lots of trades.
Exactly. While Tesla had a lot of activity during the period they studied, that might not be the case for all companies, or even for Tesla in different time periods.
So for a company with very little insider trading.
These algorithms might not have enough data to learn from to make reliable predictions. Garbage in, garbage out, as you said earlier.
Right. If there aren't enough puzzle pieces, it's hard to see the full picture. Makes sense. What else?
Secondly, the study itself acknowledges that insider trading data alone is very unlikely to be a perfect predictor of stock prices. It just can't be.
Why not?
Well, the stock market is influenced by a huge number of factors: economic news, global events, interest rates, competitor actions, overall investor sentiment.
Things way outside of what insiders are doing with their own shares?
Exactly. Stuff that isn't captured in just insider trading data. If you were to rely solely on this information, you'd be missing a massive chunk of the story.
So it's one piece of the puzzle, maybe an important piece, but definitely not the whole thing.
Precisely. The researchers emphasize that to get a more complete understanding of what's driving stock prices, it's crucial to also look at other sources.
Like,
News articles, company financial reports, earnings calls, even what people are saying on social media maybe. A much broader information set.
got it. Synthesize more data.
And furthermore, the stock market is it's constantly changing. It's incredibly complex, dynamic.
Yeah.
No algorithm, no matter how advanced, can perfectly predict future movements with absolute certainty. There will always be unexpected events, black swans, market reactions that can throw even the best predictions off.
So the key takeaway isn't that we found some magic formula for predicting the stock market. That would be nice, but no.
Huh, definitely not.
Yeah.
It's more that machine learning can be a powerful tool. It can potentially uncover valuable insights from insider trading data.
When used wisely.
Yes, wisely and in combination with other information.
So it's a tool to aid judgment, not replace it.
Exactly. As this study demonstrates, these algorithms can be really helpful in identifying patterns in data that might not be obvious to human analysts, but they should be seen as a tool to aid investment decisions, not as the only factor.
Human judgment, based on a broader understanding, still seems essential.
Absolutely essential.
Okay, so to bring it all together for you, the listener, this deep dive into the research paper shows that machine learning algorithms, particularly things like SVM with that RBF kernel and random forests, can be quite good at finding connections.
Connections between insider trading activity and, in this case, Tesla's stock price changes between April 2020 and March 2023.
And the study highlighted that things like the dollar volume, the sheer amount of money involved, and whether trades were buys or sells were particularly important signals.
Yeah, those seem to be key features.
And it also showed us very clearly that there's often a trade-off between how accurate a prediction is and how long it takes to actually get it.
That accuracy versus speed dilemma.
But, and this is a big, but it's vital to remember that while these findings are interesting and suggest some real potential,
These algorithms are not foolproof. They aren't crystal balls.
right, they're most effective when they're used as part of a larger strategy that looks at a wide range of information.
And acknowledges that the stock market is, well, a complex and sometimes unpredictable beast.
And on that note, here's a final thought for you to chew on. Given this clear trade-off between accuracy and speed that the study uncovered.
The 88% in 28 minutes versus 68% in 1 minute.
Exactly. What do you think might be the sweet spot for an individual investor or maybe someone working as a financial analyst when they're thinking about using tools like these?
Good question.
Beyond just getting the most accurate prediction as quickly as possible, what other things might they need to consider?
Maybe things like interpretability. Like, how easy is it to understand why an algorithm is making a certain prediction?
Yeah, the black box problem. Or
Okay.
cost, how much it costs to run these complex models.
Or just how well they fit into their existing workflow, their existing way of working.
It's a lot to think about, for sure. We hope this deep dive has given you a solid starting point to explore these questions further. Thanks for tuning in.